Organic molecules are molecules that are made up largely of carbon, but can also contain various other molecules and types of bonds. The reason why carbon is the fundamental basis for organic chemistry and organic molecules is because we say that carbon is tetravalent. Tetravalent refers to its valency, saying that it has 4 valence electrons and as a result is able to form 4 bonds. What makes that unique is that carbon is now able to bond with itself and form longer chains, and we call that ability carbon's ability to catenate, the ability to form long chains by bonding with oneself. And so what this does is it creates a problem in that molecules can no longer be completely defined by the traditional molecular formula. If we use a simple example, a molecule C5H12, a molecule that contains 5 carbons and 12 hydrogens, we do not know from looking at that molecular formula what the structural arrangement is, which is why it now becomes necessary for us to have a structural formula. The structural formula can show the way in which those carbon atoms are arranged with each other. The first possible arrangement here being 5 carbons arranged in a straight chain. Then there are also 2 other possible arrangements, those being 4 carbons with a single branch coming off one of the carbons, and also then 3 carbons in a chain with 2 branches coming off those carbons. As we can see here, these 3 molecules are all defined by the molecular formula C5H12, but they are completely different, which is why structural formula becomes important. And it's important to remember in structural formula that all the necessary hydrogen atoms must be drawn in. A slightly simplified version of structural formula is called condensed structural formula, where each carbon is defined by, or is shown with the number of hydrogens or various other atoms attached to it. So we say this carbon here has 3 hydrogen, this one has 2, 2, 2, and then the final carbon being CH3. The last way that we can define these molecules is called the IUPAC name. It is the International Convention for Naming Organic Molecules. And the IUPAC name can be broken down in a number of ways, but essentially what we can do if we decide to name this molecule over here, we can say this molecule has a 4-chain carbon, or 4 carbons in its longest chain, which tells us that this must get the prefix but. We can also see that there are only single bonds, which means it belongs to the homologous series called Alkanes, and as a result gets the suffix ANE, so this is butane. And then finally we can see that there is a branch coming off here of a single carbon, that meaning that there is a methyl group. Methyl, the YL, represents the fact that it's a branch, and we need to specify that that is on the second carbon. So the IUPAC name is very useful because different parts of that name tell us everything about the molecule. The root of that chain we know is a 4-carbon chain. We can see that it is an alkane, which means that it consists of only single bonds from the suffix. We can see that there is a branch represented by the YL, and we can also see that that branch is a single carbon long and is attached to the second carbon in that chain. So in conclusion, organic molecules are molecules made up of carbon that catenates to form long chains. The chains are defined by the number of carbons, where a chain containing 1 carbon gets the prefix meth, and here we can see the prefixes meth, eth, prop, but, pent, hex, hept, oct. We would typically deal with carbons chains up to 8 carbons long. We then get something called a functional group that defines the type of molecule, and then we also get branches that can be attached to that main chain. There are 4 ways in which we can express a molecule: molecular formula, structural formula, condensed structural formula, and the IUPAC name. It is important to understand the difference between a functional group and a homologous series when looking at organic molecules. A functional group is a bond atom or group of atoms that determines the physical and chemical properties of a group. of organic compounds. That group that is referred to is the homologous series, where a homologous series is a series of organic compounds that have the same functional group and can be described by the same general formula. So what this tells us is that the functional group is that bond atom or group of atoms that defines a molecule. So the simplest molecule that we find has a functional group that is a carbon-carbon single bond, and we say that the functional group is the carbon-carbon single bond, and the homologous series is the alkane. The general formula tells us that it is always CnH2n plus 2, which tells us that if you have a compound that has 5 carbons, then it would have 2 times 5 plus 2, that being 12 hydrogens, and alkanes always get the suffix ane. Similarly, a compound that contains a double bond is called an alkene and has the general formula CnH2n, which tells us that if it contains only one double bond, then it has 4 carbons, then it would have 8 hydrogens, and that would always get the suffix ene. A triple bond is the third type of functional group, and that is defined by the formula CnH2n minus 2, which says that if we had a compound that had 6 carbons, it would then have 10 hydrogens present, and it gets the suffix yne. That is the alkanes, alkenes, and alkynes. Then we get haloalkanes, that where one of the hydrogens is replaced by a halogen, the halogens being fluorine, chlorine, bromine, and iodine. And in that case, our general formula then, if we took the original alkane, would be C5H11, because one of the hydrogens has been replaced, where X represents any one of the halogens, in this example, bromine. The next type of functional group is known as the hydroxyl group, that is an oxygen single bonded to a hydrogen. And any compound that contains this hydroxyl group would belong to the homologous series of the alcohols and would therefore get a suffix anol in condensed structural formula that is represented by an OH. Next, we have what is known as the Formyl functional group, which is a carbon double bonded to an oxygen and single bonded to a hydrogen. And any compound that contains this Formyl functional group would belong to the aldehyde homologous series and therefore get the suffix anel. It is represented as CHO in condensed structural formula. Very similar to the aldehydes or the ketones, where we have the carbonyl functional group, which is a carbon that is double bonded to an oxygen, but can form 2 chains, one on either side of that carbon atom that is bonded to the oxygen. Any compound that contains a carbonyl functional group is then a ketone, and this is represented with a C with an O in brackets, and it gets the suffix anone. Then we get the carboxyl functional group, which, as we can see, is a combination of the hydroxyl group and the carbonyl group, where we have a carbon double bonded to an oxygen, also single bonded to an oxygen, which is single bonded to a hydrogen. Any compound that contains this carboxyl functional group is a carboxylic acid, represented in condensed structural formula as COOH, and gets the suffix anoic acid. Finally, the last functional group that is dealt with in NSC is the ester functional group, a carbon single bonded to an oxygen and double bonded to an oxygen, where you have 2 chains, one going off on either side of that. This is known as the ester group, and it belongs to the ester homologous series, represented by a COO, and this, because there are 2 chains, gets one of the chains gets the suffix YL, the other gets the suffix anoate. It is important to understand these functional groups, because once you understand what each functional group represents, you can immediately identify what homologous series that compound belongs to. Important to note here that any compound that contains the hydroxyl functional group, no matter how long that carbon chain is, belongs to the alcohol homologous series. Alkanes are the simplest organic compounds, as they contain only carbon-carbon single bonds and carbon-hydrogen bonds. any substance that is identified to be an alkane will get the suffix ane and be described by the general formula CnH2n plus 2. So the way that we would name an alkane is you start by identifying the longest chain in the molecule, and here we can see that the longest chain in this molecule is made up of 3 carbons. The prefix for a compound containing 3 carbons is prop, and because we can now see that this compound contains only carbon-carbon single bonds and carbon-hydrogen single bonds, we know that it is an alkane and therefore gets the suffix ane. So this compound is therefore named propane. We can see here that this compound contains 3 carbons and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and therefore abides by the formula CnH2n plus 2. We can also draw this in condensed structural formula as CH3, CH2, CH3. We can do the same for this compound here, once again identifying the longest carbon chain, where we can see that there are 6 carbons. The fact that there is a bend in the chain does not affect this, so we can see that there are 5 carbons in this longest chain, which means that it gets the prefix pent. We can then see, since there are only carbon-carbon single bonds and carbon-hydrogen bonds, it is an alkane, therefore gets the suffix ane. And we can see that this is made up of 5 carbons and 12 hydrogens, and the condensed structural formula for this would be CH3, CH2, 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 CH3. This can sometimes be written as well as CH3 followed by 3 CH2, so by putting it in brackets here we are abbreviating it, and then followed at the end by a CH3. It's important to note here that we say that alkanes are saturated because each carbon has the maximum number of bonds with different atoms, or we say it contains only single bonds. Alkenes are compounds that contain at least one carbon-carbon double bond, where we know that a carbon-carbon double bond is one in which each carbon present in the bond shares 2 electrons. Alkenes therefore get the suffix ene, and they have the general formula CnH2n. So we would name an alkene by identifying the longest chain containing that double bond, which in this case we can see is 4 carbons. We know that 4 carbons gets the prefix but. And now, because we know that this is an alkene, since it contains a double bond, we would call it butene. But we need to indicate the position of that double bond, and we always number so that the double bond, or that functional group, has the smallest number possible, which means that this would be carbon number 1, and we would call this but1ene. We would, for a more complicated molecule, follow a very similar pattern, where we first identify the longest carbon chain, keeping in mind that bends in the chain do not affect the chain length, where we can see that the longest chain here is 1, 2, 3, 4, 5, 6, 7 carbons long, which means that we get the prefix hept. We can see once again that it contains a double bond, this time 2 double bonds, but therefore gets the suffix ene, but we indicate that there are multiple functional groups with a prefix di, tri, or tetra, so this would now be diene. And finally, we must number this, we must indicate the position of those double bonds, and we again choose to number from the side that makes those numbers as small as possible, so we would call this hept 1, 4, di, saying that there are 2 ene, 2 double bonds, and that would be how we name this alkene. We would, in condensed structural formula, we follow exactly the same pattern. This would be CH3, CH2, CH, followed by CH2. It would be up to the person reading this to see that each of these 2 carbons is 1 bond short, and therefore see that there is a double bond present there. And the same pattern here, where we say that this is CH3, CH, followed by a CH again. We can see that each of those carbons is one bond short, followed by once again a CH, CH, and then CH2, and then CH3. We say that alkenes are unsaturated compounds because they contain a double bond. And once again, it is important when there are multiple double bonds, we would indicate that with di for 2, tri for 3, and tetra for 4. Alkynes are organic compounds that contain at least one carbon-carbon triple bond. We remember that a triple bond refers to a bond between, in this case, two carbon atoms where each atom donates 3 electrons, and as a result 3 bonds are formed between those atoms. Alkynes get the suffix YNE and have the general formula CnH2n-2. We would name an alkyne by counting the number of carbons in the longest chain. In this case, this chain has 3 carbons. 3 carbons we know gets the prefix prop. And we know that it should get the suffix YNE, but we need to indicate the position of that triple bond, and we always count from the side that makes that triple bond on the smallest number carbon possible, so this would be called prop 1 ine. The condensed structural formula for this molecule would then be written as CH3C CH, and then the reader would be required to see that a triple bond is necessary to ensure that each carbon has formed 3 bonds. The next one, we would follow the same pattern where we count the number of carbons in the longest chain, where a bend in the chain does not affect the chain length. So 1, 2, 3, 4, 5, 6, 7, 8. So we know that this gets the prefix oct. We can see that there are 3 triple bonds present, which means that this is going to be a tri-ine, and we indicate the position of those 3 double bonds by seeing that they are on the 1st, 4th, and 6th carbon. So we say oct 1, 4, 6, tri-ine. And the condensed structural formula for this molecule can be written as CH3 followed by a C followed by another C, 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 CH2, C, CH. And our final example here, we can see that there is a triple bond and a double bond present, which would suggest that this is both an alkyne and an alkene, but the alkyne takes preference over the alkene, so we follow the same numbering pattern. 1, 2, 3, 4. This is a bute molecule. And what we do to indicate that there is a double and a triple bond is we say that this is bute 3N1 ine, where we always number so that the main functional group, in this case the triple bond, has the smallest possible number, which is why we have numbered from the left, and we always show that there is the alkene first and the main functional group comes last. This type of question, a question in which there are 2 different functional groups, would not appear in the NSC syllabus, but this is just for interest's sake how you would answer a question like this. We can then see that each of these alkynes subscribes to the general formula CnH2n-2 by looking at prop 1 ine, seeing that that contains 3 carbons and 1, 2, 3, 4 hydrogens, C3H4, and this molecule over here would not necessarily subscribe to this formula because this formula applies when there is only 1 triple bond, and here there are 3 triple bonds, so this general formula only applies in cases where there is 1 triple bond present. And finally, it is important to remember that a compound that contains a double or a triple bond or a multiple bond is said to be unsaturated. It is only the alkanes that are saturated compounds. Alkyl halides are seen as branches of organic compounds where at least one hydrogen has been replaced by a halogen, the halogens being fluorine, chlorine, bromine, and iodine. since these are seen as branches, they are added to the name of the compound by use of a prefix. And so we would still name the carbon chain in exactly the same way, and we show that with this example here where we have 4 carbons in the main chain, therefore it gets the prefix but, and it is an alkane since there are only single bonds, so it is therefore butane. But now as we can see that by numbering from the right hand side, there is a fluorine in place of a hydrogen on the second carbon, so we would therefore name this fluorobutane, and again the position is important, so we call it 2-fluorobutane. This can now be applied to any organic compound that includes alkynes. So here we can once again follow the same pattern where we can see that this is an alkyne as a result of this triple bond. This triple bond tells us it gets the suffix YNE. We can see that the main chain has 5 carbons in it and therefore gets the prefix pent, and it is important to indicate the position of that triple bond, and that is on the first carbon, so pent 1 ine. And we can now see that there are 4 alkyl halide branches here, those being a fluorine, a chlorine, and 2 iodines. And since we have started numbering with this as carbon number 1, we must continue doing that in naming the entire compound: 4-chloro, 3-fluoro, 5,5 diiodo-pent 1 ine. A couple of things to note with this name. Firstly, the alkyne, the triple bond functional group, takes preference over all of the others, which is why we always number from the side that gives that the smallest positional number. The second thing is that we arrange these prefixes, these branches, alphabetically, where we can see that C comes before F, which comes before I. It is important to remember to ignore the prefix di, tri, or tetra. We are only comparing the first letter of iodo, fluoro, and chloro. And once we have chosen to number from the left-hand side for our alkyne, we must keep that numbering, which is why this is carbon number 3, carbon number 4, and carbon number 5. And it is important to identify that both iodines are on the 5th carbon, 5,5. It is not acceptable to leave this as simply 5-diodo-pent 1 ine. Organic compounds are often found to have branches, or what we call alkyl groups, that are attached to the main carbon chain. And there is a naming convention for how we name those branches, or once again alkyl groups. Our first step remains the same, and that is to identify the longest carbon chain possible in that molecule. So for this example over here, our longest carbon chain is 1, 2, 3, 4 carbons, which means that it gets the prefix but. We can see that it contains only single bonds and therefore is an alkane and gets the suffix ane, butane. And now what we can see is that there is a single carbon that is attached to that main chain. And so that single carbon gets the same prefix that a single carbon chain would get, but now because it is a branch, it gets the suffix YL. So this would then be called methyl butane, and that is all one word. What is once again important is to indicate the position of that branch, and we always count from the side that makes that number as small as possible. So if this is carbon number 1, then this would be 2-methyl butane. The same principle can be applied to longer molecules and multiple chains, where our first step once again is going to be to identify the longest carbon chain, where here we can see that our longest carbon chain is made up of 6 carbons. Note here that this branch at the end is not a branch because it is on the first or on the last carbon, and as a result forms a continuous chain that is 6 carbons long. We know that 6 carbons gets the prefix hex, and since it is an alkane with only single bonds, we would call that hexane. Then what we can see is there are 2 separate branches. One branch that has only a single carbon, that we would know is a methyl group, and another branch that has 2 carbons, which makes it an ethyl group. These groups must always be arranged alphabetically, so we can see here that alphabetically the ethyl group comes before the methyl group, and we must number them as 2-methyl, 3-ethyl, and so the IUPAC name for this compound is then 3-ethyl, 2-methyl hexane. That is all one word. We can do the same thing where we remember that the halogen branches are also considered branches and are therefore of equal importance. So once again, we identify our longest carbon chain, that here is 7 carbons, and therefore we are dealing with a heptane molecule, where we can now see that we have 2 methyl branches, a fluoro branch, and an ethyl branch. And once again, we arrange these alphabetically. Alphabetically, the ethyl branch would come first, and that would be a 4-ethyl because it is on the 4th carbon. There are 2 methyl branches, both of those on the 2nd carbon. And just like we did for the halogens, when there are 2 of them, we would use the prefix di. So we are going to have dimethyl here, and then a fluoro branch on the 3rd carbon, which makes the IUPAC name for this molecule 4-ethyl, 3-fluoro, 2,2 dimethyl heptane. Important to note here that even though they are both on the 2nd carbon, it is still necessary to list the number 2 twice and to indicate that with a di. Another important thing to note is that we still, when arranging them alphabetically, we still look at the M in methyl. We do not think that this is a D which should come before E. We always look at the prefix that is a result of the number of carbons in that chain. The last thing to note here is that in the condensed structural formula, branches are written in brackets. So this molecule here would be CH3 followed by a CH followed by a CH3 branch, which is in brackets, followed by another carbon that is attached to a single hydrogen, followed by a branch that is a CH2 molecule, followed by a CH3, and then a CH2 molecule, another CH2 molecule, and a CH3 to end that. So branches in condensed structural formula are written in brackets. Alcohols are the homologous series of molecules that contain what is called a hydroxyl functional group, and the hydroxyl functional group is a carbon that is single bonded to an oxygen that is in turn single bonded to a hydrogen. We always draw it at this angle because the oxygen atom has 2 lone pairs of electrons that repel the hydrogen atom into that curved or bent configuration. So any compound that contains this hydroxyl group, the functional group of the alcohols, is said to be an alcohol and therefore gets the suffix -anol. The rules for how we name compounds remain very similar from there onwards, where we would name this compound here first by identifying the longest carbon chain, which is 3 carbons, and 3 carbons we know gets the prefix prop. And now that we know that it is an alcohol because it has this hydroxyl functional group, we know it should be propanol, but it is important to indicate the position of that hydroxyl group, so we would call this propan-2-ol, which says prop tells us that it is a 3 carbon chain, anol tells us that it is an alcohol, and the 2 tells us that the hydroxyl group is on the 2nd carbon. The other rules still apply, as we would have in branches, where here we can see we once again have an alcohol because it has the hydroxyl functional group, and we start by identifying the longest possible carbon chain. In this case, that is meth, eth, prop, bute, pent. We can see that it is an alcohol, so it should be pentanol, but the change now is that there are 2 hydroxyl groups, so we would write this as pent 2,3-diol. We use the same prefixes for multiple functional groups as we had di, tri, and tetra, so this would be pent 2,3-diol, with this being carbon number 1. and then we can see that there are 2 methyl branches both on the 4th carbon, and so the complete IUPAC name for this molecule would be 4,4-dimethyl pentan 2,3-diol, and that is all one word. Important to note here that we always number an alcohol so that the hydroxyl groups are the smallest possible numbers. So we know that technically by numbering this as carbon number 1, the total number would have been smaller, but we have to number from the side closest to the hydroxyl functional group when it is an alcohol. Another important concept to understand in alcohols is that of primary, secondary, and tertiary alcohols. And we can illustrate that here by seeing that the carbon to which the hydroxyl group is bonded in this molecule here is in turn only attached to one other carbon, and as a result we call it a primary alcohol. So because the carbon to which the hydroxyl group is attached is only attached to one other carbon, we call it a primary alcohol. We can then see in this molecule here that since this carbon to which the hydroxyl group is attached to 2 other carbon atoms, we call it a secondary alcohol. And then finally, in this example here, the carbon to which the hydroxyl group is attached to 3 other carbon atoms, and as a result we call it a tertiary alcohol. This becomes important in the next section where we start looking at how alcohols react with each other. So it is important to be able to identify primary, secondary, and tertiary alcohols, and that is done by looking at the number of carbons to which the carbon attached to the hydroxyl group is attached. Aldehydes are organic compounds that contain a formyl functional group. The formyl functional group is a carbon that is double bonded to an oxygen and single bonded to a hydrogen, and then single bonded to the rest of a carbon chain. Now, any compound that contains this formyl group is called an aldehyde and therefore gets the suffix -anal. Now, what we can see, what is unique about this formyl group is that since it only allows the carbon chain to extend in one direction, we do not need to indicate the position of that formyl functional group. So we would name a compound by counting the number of carbons in the longest chain, in this case meth, eth, prop, bute. And we would then say that since it contains this formyl functional group, it is an aldehyde and therefore gets the suffix -anal, and so we would call this butanol. It is unnecessary to call it butan 1-al because aldehydes with a formyl group are always on the first carbon. We can see this with a slightly more complicated molecule, where here we identify once again our longest carbon chain. It was also possible to identify this as the longest chain, but what that would then do is create a branch that has a branch off it, and that is unnecessarily complicated for us, so we choose the longest carbon chain possible. We therefore see that this is 5 carbons and therefore pent. We can see that it contains the formyl group and therefore must be pentanal. And then what we do is, in the same way as we always would, we name the alkyl branches. Here we can see that there are 3 carbons attached to the main chain. Note here that the fact that it bends does not affect the way in which we name it. It is still 3 carbons. 3 carbons gets the prefix prop, and propyl because it is a branch, and here we have a methyl branch. And now because this is an aldehyde, this is automatically carbon number 1, and as a result the propyl branch must be on carbon number 2 and the methyl branch on carbon number 3, and so alphabetically we would call this 3-methyl 2-propyl pentanol. Once again, this is all one word. Ketones are compounds that contain what is called a carbonyl functional group, which is very similar to the formyl functional group of aldehydes, The difference being that the carbonyl functional group allows for the carbon chain to extend on either side of it, where we have a carbon double bonded to an oxygen, but carbons can be attached on either side of that carbonyl group. Any compound that contains this carbonyl group is called a ketone and gets the suffix anone, and the same naming conventions apply, where we start by identifying the longest chain that contains that functional group. In this case, that is 5 carbons, and therefore this is pent, and it would be pentanone, but it is important to indicate the position of that carbonyl group, and we can see that this is on the second carbon. We need to count from the side that makes that number the smallest, so we call this pentan to one. It is important to keep in mind that when this carbon double bonds to an oxygen, it already has 4 bonds, so it is not necessary to draw another hydrogen on. We can then do a slightly more complicated example, where here we start once again by identifying the longest carbon chain that contains that functional group. Again, do not be confused by a bend in that chain. The longest chain here, meth, eth, prop, but, pent, hex, hept. So we know that this is going to be heptanone, but it is important once again to number from the side that makes this the smallest number. So we are going to call this heptan 3 one, and then identify 1 methyl branch and 2 fluoro branches. Alphabetically, the fluoro branches should be placed first, and those fluoro branches are both on the 5th carbon, so we call this 5,5 difluoro, di to indicate the fact that there are 2 fluorines attached both on the 5th carbon, and 6 methyl heptan 3 one. It is important to see here that this is very similar to an aldehyde, but you would never have a pentan 1 one, because if it was 1 one, that would mean that the carbonyl group is on the 1st carbon, which would make it an aldehyde. So a ketone will never have a 1 in it, because if it had a 1, it would then be an aldehyde, because aldehydes have the Formyl group placed on the 1st carbon. Carboxylic acids are organic compounds that contain what is called the carboxyl group. The carboxyl group is a carbon that is double bonded to an oxygen and single bonded to an oxygen, which is in turn bonded to a hydrogen, which, as you can see, looks a lot like the carbonyl group and hydroxyl group that are attached together, which is where the name comes from. Any compound that contains this carboxyl group is called a carboxylic acid and gets the suffix anoic acid. So we would name this compound here by identifying our longest carbon chain as having 2 carbons, therefore eth, and with this carboxyl functional group, we say it must be a carboxylic acid and is therefore ethanoic acid. And now, for the first time in organic chemistry, we are naming something with 2 separate words, ethanoic and acid, with a space between those words. The naming conventions remain the same for molecules that include branches. Here we can see the longest carbon chain is 3 carbons, that being prop, and as a result we would call this propanoic acid, since it has a carboxyl group attached to it. Again, that is written as 2 words. And then we would see that once again the carboxyl group must always be on carbon number 1, which means that this methyl branch is on the 2nd carbon, and we would call this 2-methyl propanoic acid. Esters are organic compounds that contain the ester group, which is a carbon that is double bonded to an oxygen and also single bonded to an oxygen, with 2 separate carbon chains that go off in separate directions. When a compound contains this ester group, it is said to be an ester and gets the suffix in 2 words, YL and anoate. And it's important to be able to identify which part gets which suffix. So the first thing that you need to do is identify the ester functional group when naming a molecule, and here we can see that we have the ester functional group. We can see that this is broken up into 2 parts. There's one part of this molecule that is attached only by a single bond to the oxygen. That is always seen as the branch to this ester, and as a result comes first and gets the suffix YL. So in this case, that is 2 carbons, meth, eth. So we would call this ethyl. This is also 2 words, and the second part of this compound is 3 carbons attached to that ester group, which ends in that carbon-oxygen double bond, and that 3 carbons gets the prefix prop and suffix anoate. Once again, as a result of the structure of this, it is not necessary to name where this takes place or give a number. We can do that with one more example. We first identify the ester functional group, and then we identify the part of that functional group that is attached by a single bond to the oxygen. In this case, we can see that that is a 5-carbon chain, which means that the part that gets the suffix YL is meth, eth, prop, but, pent. So we would call this pentyl. And then the part of this compound that is attached to the double bonded oxygen is always the main part, and that gets the suffix anoate, meth, eth, prop, but. So this would then be correctly called pentyl butanoate. Physical properties are properties that can be measured, and there are, largely speaking, 4 physical properties that we deal with. The first 2 are melting point, which is the temperature at which the solid and liquid phases of a substance are in equilibrium, and boiling point, which is the temperature at which the vapor pressure of a substance equals the atmospheric pressure. And we know that in a solid, the particles are densely packed and fairly neatly arranged. In a liquid, they are still fairly densely packed, but the arrangement is random, and in a gas, the particles have large distances between them, and there is absolutely no arrangement. And in order to separate or to convert from a solid to a liquid or a liquid to a gas, it's necessary to break the intermolecular forces that exist between those molecules. So what we find is that substances that have stronger intermolecular forces will have higher melting and boiling points. The third physical property is called vapor pressure, and that is the pressure exerted by a vapor at equilibrium with its liquid in a closed system. And what we find here is that there are always a certain number of particles that are able to escape from a liquid and become a gas, and in a closed system, that gas exerts a force on the container. Now, a substance that has strong intermolecular forces would not easily allow particles to escape, unlike a substance with weak intermolecular forces where the particles are able to easily escape that liquid and become a gas. So what we find is that substances with weak intermolecular forces have more gas particles, and as a result a higher vapor pressure. And so we can summarize as this strong intermolecular forces result in a low vapor pressure. The fourth and less common physical property is viscosity, which is the resistance of a liquid to flow, where a substance like honey would have a very high viscosity because it is very resistant to flow, and a substance like water would have a very low viscosity because it flows very easily. And that flow is essentially a measure of how strong the intermolecular forces are between particles. If the particles are held together by strong intermolecular forces, the substance does not easily flow, and as a result we say that strong intermolecular forces result in a high viscosity. Hydrocarbons are always considered to be non-polar molecules because they contain only carbon-carbon single bonds, which have an electronegativity difference of 0, and carbon-hydrogen single bonds, which have an electronegativity difference of 0.4. Both of those are considered to be non-polar bonds, and as a result, hydrocarbons are always non-polar molecules, and as a result, the only intermolecular forces that exist between hydrocarbons are the London dispersion forces. So there are two ways in which we can compare molecular polarity and intermolecular forces in organic molecules. The first is for molecules that have the same chain length, the only difference would then be the functional group. And so we would compare the polarity of different functional groups. And here I have laid out in a table in order of increasing polarity. So as we have said, hydrocarbons are non-polar molecules. The halogens, iodine and bromine, are also non-polar because they have such a small electronegativity difference, those being 0 and 0.3 respectively, that we say that any molecule containing one of these groups is also non-polar, and as a result, the intermolecular forces are London forces. The chlorine functional group is said to be weakly polar because it has an electronegativity difference of 0.5. As a result of this weak polarity, we say that the intermolecular forces that exist between molecules that contain this group are weak dipole-dipole forces. The next functional group that we look at is the carbonyl group that makes our ketones, and that because of the carbon-oxygen bond, which has an electronegativity difference of 1, we say that that is a polar molecule, and as a result there are dipole-dipole forces. Next comes the ester group, which is also polar and dipole-dipole forces, followed by the Formyl group of aldehydes, which is also polar, which gives rise to dipole-dipole forces. It's important to note here that these are arranged in order of increasing polarity, but they are all very, very similar in their polarity. The next big increase is that of a fluoro group because it has an electronegativity difference of 1.5, and as a result, we say that is a polar bond, which makes it a polar molecule, which makes those dipole-dipole intermolecular forces that are stronger than those containing the carbon-oxygen double bond. Second to last, we have the hydroxyl group of alcohols, that is an oxygen bonded to a hydrogen, which is a very polar group, and as a result we have not only dipole-dipole forces but hydrogen bonding intermolecular forces, and so as a result those are very strong. And finally we have the carboxyl group of our carboxylic acids, which is our carbonyl group and the hydroxyl group, which makes this even more polar than the hydroxyl group on its own, which makes these hydrogen bonding forces the strongest. So as we can see in this table, we have arranged these functional groups in order of increasing intermolecular force strength. And so we can say that substances with functional groups lower down on this table have stronger intermolecular forces, and as a result their physical properties would be affected. Hydrocarbons are always non-polar organic molecules because of the non-polar carbon-carbon and carbon-hydrogen single bonds, and as a result the only intermolecular forces that exist between hydrocarbons are the London forces. So in a situation where two or more molecules have the same functional group, in this case being hydrocarbons, then all that needs to be compared is what is called the contact surface area, where contact surface area refers essentially to the size of the molecule, but more specifically to the amount of places on the molecule where intermolecular forces can exist. And there are three properties that are said to influence the contact surface area. The first is the length of the chain, or the chain length, also sometimes referred to as the molecular mass, where here we can see we have two examples. The first example is a smaller molecule that only has 1, 2, 3, 4, 5, 6 sites where intermolecular forces could exist, where those temporary dipoles of London forces could be induced. This is in contrast to a bigger molecule that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sites for potential London forces to exist, and as a result we say that this chain length being longer gives it a greater contact surface area, and therefore we say that this molecule would have stronger intermolecular forces than this one. It's important to note that we are not saying that these are different intermolecular forces. Both of these molecules only have London dispersion forces between them, but this one would have more opportunities for London forces to exist, and as a result those forces would be stronger. The second property is called branching, where if we compare three molecules that have the same molecular mass, these being isomers of each other, we can see that each one of these molecules gets a single carbon shorter as we add a branch. And what we say branching does is it decreases the contact surface area because there are molecules and atoms that are too close together to allow for sites for intermolecular forces to exist. And as a result of that, we say that as the amount of branching increases, this contact surface area decreases. That decreasing contact surface area therefore allows for fewer London forces to exist and results in weaker intermolecular forces. So we would say the molecule with the least branching, the longest straight chain, is going to have the strongest intermolecular forces, once again those still only being London forces. The third possible change is the bond order, and bond order refers to multiple bonds, those being double or triple bonds. So what we can see here, we have three carbon chains, each of them with three carbons in them, but the first carbon chain does not have a single double bond in it. The second carbon chain has one double bond and the third carbon chain has two double bonds. And what we say is that these multiple bonds, double or triple bonds, increase the rigidity. They make this molecule more rigid and less flexible, which as a result causes fewer sites or fewer interactions between molecules, basically decreasing the number of possible sites for London forces to exist. So we say it decreases the contact surface area once again. And so we say that as the bond order increases, as the number of multiple bonds increases, the intermolecular forces get weaker because the molecules become more rigid. There is a standard approach that is required to compare the physical properties of different organic molecules. And that approach is 4 steps that need to be gone through. The first one is to identify the differences between the molecules, whether those are functional groups or contact surface area differences. The second step is to compare the intermolecular forces that exist between each molecule. The third is to relate those intermolecular force differences to energy. And finally, then compare, using that energy relation, that to a physical property. There are largely 2 categories in which these questions happen. The first is where you're given 2 molecules, 2 or more molecules that have the same chain length but different functional groups. We've got an example here of an aldehyde that has a Formyl group on it and an alcohol that has a hydroxyl group on it. And we can see how we go through this approach. The first step is to identify the differences. That is to say that the aldehyde has a polar carbonyl group on it, where the alcohol has a very polar hydroxyl group. The second step is to compare those intermolecular forces. So we would say that the polar aldehyde has dipole-dipole intermolecular forces which are weaker than the hydrogen bonding intermolecular forces that exist on the alcohol. The third step is to relate that intermolecular force difference to energy, and that is done in the following way. It is done by saying the stronger hydrogen bonding forces require more energy to separate. And then your final step would be to say, therefore, since more energy is required, the alcohol would have a higher melting point or boiling point or viscosity or a lower vapor pressure than the aldehyde. The second type of question that can come across is one where you have 2 or more molecules that have the same functional groups, but they have different chain lengths. And here I've got an example of a carbon compound that contains, or a hydrocarbon, with 2 carbons and a hydrocarbon with 5 carbons in its chain. And the first step here is to once again identify the differences, and we would state here that they are both alkanes or both hydrocarbons, but one of them is a 2 carbon chain where the other is a 5 carbon chain. The second step there is to compare the intermolecular forces, and we would start by stating that since they are both hydrocarbons, that they both have London forces acting between them. However, since the 5 carbon chain has a greater contact surface area than the 2 carbon chain, therefore the 5 carbon chain would have stronger intermolecular forces that exist between it than the 2 carbon chain. Note once again that we are saying that it has more London forces. We are not saying that it doesn't, or it has different intermolecular forces. We are just saying that there are more of them, and as a result, stronger intermolecular forces. The third step then, once again, to relate that to energy. So to say, since the 5-carbon chain has a greater contact surface area and therefore stronger intermolecular forces, it would require more energy to separate the 5-carbon molecules than the 2-carbon molecules. And then finally, the fourth step remains exactly the same, where we would state that since more energy is required to separate the 5-carbon chain than the 2-carbon chain, it will have the higher melting point, boiling point, or viscosity, and the lower vapor pressure. Hydrogenation through addition is the addition of hydrogen to an alkene or an alkyne to produce an alkane. This reaction can only happen under very specific conditions, those being that the unsaturated compound must be dissolved in a nonpolar solvent and a platinum, nickel or palladium catalyst must be present. As an example, we have here prop-1-ene, which is an unsaturated compound because it contains a double bond that is reacted with hydrogen or a hydrogen molecule, again under these specific conditions. And under these conditions, the double bond between those two carbons would break, which would leave an additional bond able to be formed on each of those carbons, and those bonds then form with the individual hydrogens from that hydrogen molecule, which results in that prop-1-ene ending up as propane. This is an addition reaction because it is an unsaturated compound that is converted into a saturated compound, and we say it is hydrogenation through addition, and it is very specifically only possible under these two conditions. Halogenation through addition is the addition of a halogen to an alkene or an alkyne to produce a haloalkane, where the alkenes are the group 17 elements, those being fluorine, chlorine, bromine, and iodine, all of them being diatomic. Important to note that halogenation through addition has no specific conditions, and as such we would say that it would occur almost spontaneously. As an example here, we have but-2-ene, where we have a double bond on the second carbon that reacts with chlorine, and we know that this happens because the double bond, the second bond, is not as strong as the first, and as a result that bond would break, and those bonds would then form with chlorine, and we would form 2,3-dichlorobutane, and that is halogenation through addition. One of the common applications of this type of reaction is known as the bromine water test, where bromine is a brownish color, and so when we add bromine water to a saturated compound being a compound that does not contain double bonds, there is no reaction. And because there is no reaction, the water would remain a brownish color. Whereas when we add bromine water to an unsaturated compound being one that contains a double or triple bond, there would be a halogenation reaction that takes place. As a result, the bromine would be removed from the water and the solution would turn clear. And so we can use the bromine water test to test for saturated or unsaturated hydrocarbons. Hydrohalogenation through addition is the addition of a hydrogen halide to an alkene or an alkyne to produce a haloalkane. This reaction can only happen on condition that there is no water present, and as an example here we have prop-1-ene that contains a double bond on the first carbon that reacts with hydrogen fluoride, and when there is no water present we know that the second bond would break because the second bond is weaker than the first, which leaves each of these carbons willing or looking to form a bond with either hydrogen or fluorine. Now what we can see is that there are two possible products, the one being 2-fluoropropane, where the fluorine has attached to the second carbon, the other being 1-fluoropropane. And so in addition reactions for cases such as this, we use Markovnikov's rule, which says that the hydrogen will always attach to the carbon that has the most hydrogens. So in this case, we can see that the first carbon already has 2 hydrogens, and as a result, this first carbon would gain another hydrogen, and the fluorine would then be attached to the second carbon. So we say that 2-fluoropropane is the main product, and 1-fluoropropane is a byproduct, but when writing this reaction down, we typically only show it with the main product, because that is what is given by Markovnikov's rule. Hydration through addition is the addition of water to an alkene or an alkyne to produce an alcohol. This can only happen on condition that there is water present in excess, as well as a strong acid, that being either sulfuric acid or phosphoric acid. As an example, we have here butene, which has a double bond on the first carbon, and when combined with water with these conditions, that being excess water and a strong acid presence, we break the double bond on that first carbon, which leaves each carbon looking to form new bonds. The water molecule then also breaks up into a hydroxyl group and a hydrogen ion, which can then attach themselves onto those carbons. And once again, we have 2 possible products. The first product here being butane-2-ol, where the hydrogen has attached to the first carbon and the hydroxyl group has attached to the second carbon. And the other product possible being butane-1-ol, where the hydroxyl is attached to the first carbon and the hydrogen attached to the second carbon. We can determine that the butane-2-ol is the main product by Markovnikov's rule, which tells us that the hydrogen will always attach to the carbon with the most hydrogens. So as we can see, this carbon, carbon number 1, already had 2 hydrogens to start with, where carbon number 2 only had 1 hydrogen. So as a result, we would say that butane-2-ol is the main product because the hydrogen has attached to the carbon with the most hydrogens by Markovnikov's rule, which leaves the hydroxyl to the second carbon. And we would draw this as butene plus water reacts to form butane-2-ol. We do not necessarily show butane-1-ol as a byproduct. Dehydrogenation through elimination is the elimination or removal of a hydrogen molecule from an alkane to produce an alkene. Theoretically, it is also possible to remove a hydrogen molecule from an alkene to produce an alkyne, but for the purposes of this syllabus, we only do alkanes to alkenes. The only condition required for this reaction to take place is that the reaction or the reactants must be heated, and we show that by drawing a triangle underneath the arrow. So as an example here, we have butane, and butane, when heated, would lose 2 hydrogens or undergo a dehydrogenation reaction. The question of which hydrogens to remove is answered by Zaitsev's rule, which tells us that we remove the hydrogen from the carbon that has the fewest hydrogens. So that is going to be, in this case, the second carbon. We remove our first hydrogen, and then we can see on the third carbon there's also only 2 hydrogens, whereas on the first carbon there are 3 hydrogens, and since we must choose 2 consecutive carbons, we would remove the hydrogen from the second and third carbon, which gives us as our main product butene, where now that these 2 carbons have lost their hydrogens, they now form a double bond or a second bond with each other, which turns this into an alkene, and then obviously we have our hydrogen molecule as a product as well. It is also possible, and very rarely or occasionally happens, that a byproduct is formed where Zaitsev's rule is not followed, but once again, we always draw, when we're drawing this reaction, we would only show the main product and hydrogen that are formed here. Dehydrohalogenation through elimination is the elimination or removal of a hydrogen halide from a haloalkane to produce an alkene. This reaction can only happen on condition that there is a strong base present in ethanol, that strong base being either potassium or sodium hydroxide, and that this solution is heated under reflux. Under reflux refers to it being in a closed container. So as an example here, we have 2-iodobutane, and when this is placed in a strong basic solution in ethanol and heated under reflux, we find that we are able to remove an iodine as well as a hydrogen atom, and we use Zaitsev's rule once again to determine which hydrogen atom is removed. And Zaitsev's rule tells us that we will always remove the hydrogen atom from the carbon that has the least or the fewest, which over here is this carbon, as this carbon only has 2 hydrogens, and as a result our main product would then be but-2-ene, as well as obviously the hydrogen iodide that is formed. A byproduct, one that is formed not by Zaitsev's rule, but-1-ene, does exist but happens very rarely, and so as a result when we write this equation out we would write that 2-iodobutane reacts to form but-2-ene and hydrogen iodide. We do not need to specify what the byproduct is. Dehydration through elimination is the elimination or removal of water from an alcohol to produce an alkene. This reaction can only happen on condition that there is a strong acid present. That acid acts as a dehydrating agent. Usually we would use sulfuric or phosphoric acid, and that the reaction solution is heated, once again shown with the triangle underneath the arrow there. So as an example here, we can see that butane 2-ol can undergo this dehydration through elimination reaction, provided that these conditions are met, and we see that the hydroxyl group will be removed as well as a hydrogen atom. We can see that there are 2 possible hydrogen atoms that could be removed as they are adjacent to that hydroxyl group, and once again Zaitsev's rule tells us that we would remove the hydrogen from the carbon with the least or the fewest hydrogens, which means that our main product, the product that would be produced the majority of the time, would be but-2-ene, where that hydroxyl and that hydrogen are removed, and those 2 carbons form a double bond to make sure that each of them has formed 4 bonds. And so we say that the main product is but-2-ene. A possible byproduct would also be but-1-ene, and once again we would normally only write this reaction by showing these reagents. It is not necessary to show the byproduct, and then obviously we have here produced water or eliminated water, which is why this is called a dehydrating reaction. Esterification can also be called a dehydration through elimination reaction because it also eliminates or gives off a water molecule. The esterification reaction, the general word equation, says that it is an alcohol plus a carboxylic acid that reacts to form an ester and water. The conditions are the same as a normal dehydration through elimination reaction, in that a strong acid, either sulfuric or phosphoric acid, is required as a dehydrating agent, and the solution is required to be heated. So in an esterification reaction we have an alcohol. In this example we have propan 1-ol that reacts with a carboxylic acid. Here we have ethanoic acid, and the alcohol is then seen to lose its hydrogen of the hydroxyl group, which combines with the hydroxyl group of the carboxylic acid that goes to form the water molecule that is removed, and then the remainder of these 2 molecules attach to each other in the form of an ester, which we call propyl ethanoate. The propyl, the part that is attached to the single bond oxygen, is always the part that comes from the alcohol, and the part that is attached to the single and the double bond oxygen is always a result of the carboxylic acid. And so as we can see in this reaction, because there is also a water molecule given off, we can also call this a dehydration reaction. Cracking is considered to be an elimination reaction because it sees us starting with a saturated compound and ending with one or more unsaturated compounds, which is roughly the definition for an elimination reaction. There are two types of cracking. The first type is where an alkane is broken into a shorter chain alkane and an alkene, or a number of alkenes. As an example here, we have pentane that under the right conditions is broken into a propane molecule, and then because there is now a shortage of hydrogens, the shorter chain, in this case the ethene, forms a double bond. So the first type of cracking is where a alkane is broken up into an alkane and then an alkene. The second type of cracking is where an alkane is broken into one or more alkenes and hydrogen is produced as a product. So as an example here, we have hexane, the alkane, that can be broken in two ways. The first way that we've shown here is where it breaks into two molecules, each of them forming a double bond, and then because there are now two double bonds, it means that there are excess hydrogens, and so we say that hydrogen is produced as a byproduct there. The second option would be for hexane to break instead of into two pieces, but to break into three two-carbon chains, three ethene molecules, which then, because of the excess hydrogen, then produces two hydrogen molecules. It is not possible, it is not required for you to be able to determine where the break would happen. Normally what would happen is a question would say something like hexane is broken into prop 1-ene, and then you are asked to identify what the other products are. So it is not necessary for you to be able to determine where it is broken or in what form the cracking takes place. That will always be made clear to you. All that you need to know is that there are two ways in which a molecule can be cracked. That is either into an alkane and an alkene, or into alkenes and hydrogen. The conditions depend on the type of cracking. The first type is known as thermal cracking, and that requires a high temperature and a high pressure. The second type is known as catalytic cracking, and that requires a catalyst. A substitution reaction is a reaction in which an atom or a group of atoms is replaced by another atom or group of atoms. Halogenation through substitution is the specific substitution reaction where an alkane is converted into a haloalkane, where we know that the halogens are the elements found in group 17 of the periodic table, those being fluorine, chlorine, bromine, and iodine. In order for this reaction to take place, the specific condition is that the reaction must either be heated or there must be UV light present. So we know that heating a reaction we show with a triangle underneath the arrow, or UV light is shown with the symbol HF. So as an example here, we have the halogenation of propane, where the propane is going to exchange one of its hydrogen atoms for one of the bromine atoms here. And that means that there are then two products possible, that being 2-bromopropane, where a hydrogen on the second carbon has been replaced by a bromine, and then one of the products there being hydrogen bromide. Or another possible product is 1-bromopropane, where a hydrogen on the first carbon has been replaced, and then obviously hydrogen bromide still as a product. And to determine which is the main product, we use Zaitsev's rule, which tells us that we will always remove a hydrogen from the carbon that has the least or the fewest hydrogens, which means that we are always going to remove, in this case, from the second carbon, which makes the main product 2-bromopropane, and the byproduct 1-bromopropane. And again, when we write this reaction down, we only need to include the main product and hydrogen bromide for the halogenation through substitution reaction. Hydrolysis through substitution is the conversion of a haloalkane into an alcohol, and there are two ways in which that can be done. The first is with sodium hydroxide or potassium hydroxide. The specific conditions required for this type of reaction are firstly that the haloalkane must be dissolved in ethanol. Second, there must be water present, and sodium hydroxide or potassium hydroxide, and the reaction solution must be heated, again demonstrated with the triangle underneath the arrow. So in this example here we have 1-fluoroethane that reacts with sodium hydroxide, and in the correct conditions, these three conditions here, what we would find is that the fluorine atom is substituted with the hydroxide, the hydroxyl group of atoms to form ethane 1-ol, which is our alcohol, and then the remaining sodium fluoride. The second type of hydrolysis through substitution reaction is with only water, not with sodium hydroxide or potassium hydroxide. The specific conditions for this type of reaction are firstly that the haloalkane must be dissolved in ethanol, same as the previous reaction, and that there must be water present in excess. So in this example we have 2-chloropropane that reacts with water, and when these conditions are met, we find that the chlorine atom is replaced or substituted by the hydroxyl group from the water molecule, which forms the alkyl propan 2-ol and then leaves us with HCl. Interconversion through substitution is the conversion of an alcohol into a haloalkane, most often using hydrogen bromide or hydrogen chloride, and this reaction can take place on condition that there is no water present. This reaction most commonly occurs with tertiary alcohols, that is an alcohol to which the hydroxyl group is attached to a carbon that is in turn attached to 3 other carbons. And what would happen in this interconversion reaction is the hydroxyl group that is forming that tertiary alcohol would be replaced or substituted with the halogen, in this case bromine, that is attached to the hydrogen, and that takes us from 2-methyl-butane 2-ol, the alcohol, to form 2-bromo-2-methyl-butane, as well as water. This interconversion reaction can often be seen as a reverse hydrolysis reaction, where hydrolysis converts from a haloalkane into an alcohol, interconversion converts from an alcohol into a haloalkane. Plastics and polymers is a section of organic chemistry that deals largely with macromolecules, which are molecules that consist of a large number of atoms. And specifically a polymer is a large molecule composed of smaller monomer units that are covalently bonded to each other in a repeating pattern, where a monomer is a small organic molecule that can be covalently bonded to another in a repeating pattern, and a repeating unit is the smallest unit that can be repeated to create a polymer. So the way that this works is that you would start with a monomer, which, as the definition states, is an organic molecule in itself, but what makes it special or unique is the fact that it can become a repeating unit. So here we have a monomer called ethene, which is 2 carbons double bonded to each other with 4 hydrogens, but that can become a repeating unit by breaking the double bond between those 2 carbons. When that happens, each carbon is now looking to form another bond, and so these repeating units can attach themselves to each other to form a very, very long chain, also referred to as a macromolecule. Now, because we often do not want to or are not able to write out how many carbons exactly make up this macromolecule, we often write it in its polymer form, where we show the repeating unit in brackets with a number n, which is an integer number that says how many repeating units there are. So once again, with the monomer ethene, we can, by breaking that double bond, create a repeating unit that can repeat itself in number of times, which creates a polymer called polythene. The reaction that is required for this is called polymerization. There are a number of important monomers to know. The first one is vinyl chloride. So the monomer that contains a carbon-carbon double bond and 3 hydrogens and 1 other atom or group of atoms is referred to as vinyl. So vinyl chloride says that that other atom is a chlorine atom. And so when this monomer unit is converted into a repeating unit and therefore a polymer, vinyl chloride becomes polyvinyl chloride, or PVC, which is the plastic that we use in most shopping bags. Another example of a monomer is vinyl benzene, where here we have a benzene ring attached to that carbon, and when this is arranged into a polymer or a macromolecule, it becomes polystyrene. A third example is vinyl acetate, where we now have an acetate group of atoms attached to that vinyl molecule, which when repeated in a unit becomes polyvinyl acetate, or PVA, and the same goes for the monomer vinyl alcohol, which becomes polyvinyl alcohol. It is important to understand the difference between a monomer, which is the unit that can exist on its own, and a repeating unit, which just shows how these attach to each other, and then when they are placed in a bracket with an integer on the outside, that becomes the polymer that refers to how long that molecule is, by indicating how many of those repeating units are attached end to end. Polymerization is a chemical reaction in which monomers join to form polymers, and there are two types of polymerization reactions. First one being the simple addition polymerization, where very simply the double bonds on a monomer break, which allows bonds to form between the repeating units. So as an example here, we have the repeating unit that is obtained from the monomer vinyl chloride, that being 1-chloroethene, and when that double bond breaks, it forms, or it allows a radical to form on either side of the carbon, which allows those carbons to look for bonds, which then allows those carbons to attach to each other in an ever-growing chain that goes on to form a polymer. So the addition polymerization starts out with the double bonds on the monomer breaking, which allows it to form these repeating units that can then attach to each other and go on to form the polymer polyethene. The second type of polymerization reaction is the condensation polymerization, and this example here shows that there are two steps to this process. The first step being the alcohol combining with a carboxylic acid in the process we know to be esterification, and specifically this being ethane 1,2-diol combining with ethanedioic acid. That goes on to form what is called a dimer, which is essentially a molecule that consists of two monomers and water. These two monomers can then combine with themselves in a very similar way to the addition polymerization, the difference here being that as they combine, there's a hydroxyl group and a hydrogen ion that is eliminated at each combination, and as a result we form water, or water is condensed out of this polymerization reaction, and we have once again an ever-growing molecule. And in this case, what we can show here is we can show the repeating unit over here. We say that there are n number of this repeating unit in the polymer, and along with this polymer we are also going to form 2n molecules of water. This is the polymer polyester.